Okay, so this is going to be a video about more sophisticated kernel tests. We're computing more kernels for more waves, for more arrivals, and we're uh, trying to find out if there's any kind of problems with the kernels computed using SW4. And I had a kernel test video uh, about in the January of this year, I think, and this is gonna be an update to that kernel test video, and the code has changed quite significantly, and lots of new codes has been added, and then there's a new workflow for computing the kernels, um, and we're gonna look at one example that's for a uniform half space. So the geometrical setup is still the same as my previous kernel test. So it's a uniform half space structure model, and then we have a source that's located on the left side of the volume and a receiver that's on the right side of the volume. So this is actually a cross-section view that's going through the source and the receiver. And uh, these are data sensitivity kernels for broadband cross-correlation travel time. Misfits that's measured on the direct arriving P, and then a surface reflected P, so PP, right? And then a surface converted PS, so it goes up as a P and then goes down, reflects by the free surface, uh, and then goes down as an S wave, right? So these three columns are for program cross-correlation travel time with respect to P velocity. Those are kernels with respect to P velocity, and this last column is with respect to the S velocity, right? So um, so for the P converted to S, for P sensitivity, you only see the leg that's going up to the free surface. You don't see the leg that's coming down, because the wave that's coming down to the receiver is actually from the free surface to the receiver is actually an S wave. So you don't see its P sensitivity. But once you compute the S sensitivity, the sensitivity to the S velocity, you're going to see the leg that's coming down from the free surface to the receiver, right? And you can sort of see some differences, right? So this is the top row, and the bottom row are for some kind of slightly different configurations. I will try to explain that later on, right? But let's look at the how the code actually works. Let's look at the current state of the kernel codes, right? So again, this is on Xiaoyan. That's the big computer at the Anchor Wyoming Supercomputing Center, and we're doing this experiment inside of this particular directory called kernel examples SW4 half space. And then I've got a bunch of directories that's underneath this half space directory. So I've got jobs, forward wave field, FWF, KER kernel, and then VM, that's the velocity model, right? So that's some basic directories. And then if I go into FWF, I'm gonna see the directories for each source and then each receiver. So this is gonna be the source ID, right? And for now, I'm just using this one source. And then if I go into this source directory, I'm supposed to see a bunch of files. So all those WF files are actually strain fields, strain and velocity fields that's computed by SW4. Right, so those are output files. So before we actually run the SW4 code, the only file that's inside of this directory is going to be the input file to SW4. That's this file, and then this file. This file is a control file for the inversion, part of the code. And then this is the actual soft link that's linking to this particular text file inside of this jobs directory, right? And then if I look at this particular file, imv.in, it's gonna have it's an ordinary text file, and then it's got this kind of a basic information inside of it. So write info is actually a flag that's controlling the level of output that's used for inversions. So write info can have 4 different values: 0, 1, 2, or 3, right? 4 different kinds of values. So if write info equals to 0, if this number is 0, then it's just gonna run SW4 without any kind of output that's gonna be used by inversions, right? It's just a normal SW4 wave propagation simulation. It doesn't actually change anything. So when writing info equals to 0, the output or the procedure is pretty much identical to SW4. There's no change at all, and there's no output that can be used for computing the kernels. Right. So then when write info equals to 1, the simulation is not going to run till the end. It's going to be interrupted. And then you're going to see some kind of error output, but the error output doesn't really matter, right? Because the simulation was interrupted in the middle. And then what you're going to see is a bunch of output information that's going to, all the output files are going to be inside of the VM directory. So you're going to see a bunch of output files that's going to look like wf something something dot info. And then the number of files that you're going to see are going to depend upon the number of processes or the number of MPI processes that you have used to run the SW4 simulation. So inside of those files, inside of those .info files, it's going to write out the grid information, the simulation grid. Right. So if I want to sort of take a look at say cat, so wf0000000.info, right? So it's going to write out the grid information for each of the process. So what it means that SW4 is going to have different grids. It's a composite grid, right? So the first number is going to be the grid ID, right? Usually the bottom grid is grid 0, and then the top grid is going to have the largest grid number, right? That's the grid ID. And then the starting grid number for this grid ID. So on process 0000000, the grid for grid 0 is gonna, the X grid for grid 0 is gonna go from 1 to 20, and the grid range for the Y grid is gonna go from 1 to 19, and then the grid range for Z grid is gonna go from 1 to 250. Right? That's like the grid range on each of the processes, right? So if you set write info to 1, it's going to write out this wf.info, and then it's going to write out this z file. This z file is for storing the topography or the mesh, the grid, the z grid of the top grid, the z coordinate of the top grid. So when you are using a uniform grid, there's no topography, right? So these files are pretty much empty. It's just gonna store some grid number information, sort of describing the fact that there's no topography, right? So these files are gonna be very small. But if there is a topography, the curvilinear grid is gonna have non-uniform grid spacing. The curvilinear grid on the top grid, the top curvilinear grid is going to have non-uniform Z grid spacing, right? The X and Y grid spacing is still going to be uniform, but the Z grid spacing is not going to be uniform for the top curvilinear grid, right? And then the Z coordinates are going to be stored in these files, right? So these Z files are kind of important later on if we want to compute the kernels inside of the curvilinear grid. Right, these Z files are very important because it stores the curvilinear z-coordinates for the covariant grid. And then one more file that's going to be written out is grid.info, this file, right? And then if I take a look at this file, grid.info, it's going to look like this kind of thing, right? So so it's the bottom depths of each of the grid followed by the grid spacing, the grid spacing of each of the grid, right? It's a composite grid, so it's um, each individual grid is going to have a bottom depth that's in meters, right? For now, I don't have multiple grids. I have just one grid, and the grid ID is 0. So the bottom depth is going to be 49,800, right? It's going to be like close to like 50 kilometer, right? So it's a 49,800 meter, right? And then the grid spacing is going to be 200 meters. So if I have multiple grids, say suppose I have like 3 grid in my SW4 simulation, then I'm gonna have 3 depths, and those depths are gonna be the bottom depths of each of the grid, each of the individual grid, and then I'm gonna have 3 grid spacings. That's gonna be the grid spacing for individual grids, right? So it's always gonna be like this. The lines with depth information, bottom depth information, followed by the lines of the grid spacing information, right? So that's the grid info, and then that's it. That's gonna be all the output if the right info equals to 1, right? And then at that step, at that point, I have to actually go into the VM directory, and then I will need to actually run a sequential code, which is called URG. URG stands for Uniform Recording Grid. So the simulation grid used by SW4 is going to have this kind of grid spacing, right? But this kind of grid spacing is probably too small for the inversions. The inversions are going to be carried out on a coarser grid, right? And the coarser grid is called the recording grid. And this recording grid is a decimated version of this simulation grid, right? And this URG uniform recording grid is just going to create a bunch of text files that's going to describe the recording grid, right? Which is a subsample, or it's a subset of the simulation grid, right? And this URG is going to take 2 inputs. One input is the inv.in file. That's this file. That's this file that we're actually looking at. This particular file, right? So it's going to take, and so that's the first command line input, and then the second command line input is called AWP, right? So the recording grid is going to be organized in a way that's kind of similar to the AWP code, right? So before SW4, I was using a code that's called AWP. I was using a wave propagation simulation code that's called inelastic wave propagation. That's written by Kim Olsen initially, and then modified or improved, optimized for large-scale simulations by Kim Olsen's group, by Yifeng Cui's group at San Diego Supercomputing Center. So that was the finite difference, staggered grid finite difference simulation code that I was using before. And then I have some kind of a grid convention that's kind of attached to that particular simulation code. And then when I do the inversion, at least for now, I'm still sticking with that previous grid organization convention. So the second option is just called AWP. I'm sticking with the recording grid format that I was using before, right? But later on, I might change that, right? Makes the organization of the grid sort of more native to SW4. But for now, let's just run this code, and then it's gonna create this sequential code is gonna create lots of it's gonna create a bunch of files that's called GRD REC followed by the process RD. Grid recording and then followed by process ID. All these are actual text files, and the content of the text file is just first the grid number, the total number of grid for that the total number of recording grid for that particular process ID, and then the 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 the, the grid ID, the XYZ grid ID for that particular process ID. So it's gonna record first X, first Y, 250 is Z, first X, third Y, and then 250 is Z, right? It's going to be organized like that. So if there's multiple grid, you're going to see multiple these kind of lines, right? The grid number lines. The grid number lines are just for each individual composite grid, right? So if I have like three individual grids in my SW4 simulations, then I'm going to see three lines like that, and each line is going to be the number of recording grid for each individual grid, and then followed by all the grid IDs. So once the URG code, this sequential code is finished running, I can go back. I can go back to my wave propagation simulation code, and then I can modify this inv.in file, and then I can change the write info from 1 to 2, right? And then run the code, run SW4 again. And this time SW4 is not going to run to the end either, right? But it's going to produce some additional files, some additional output files that's going to be used by the inversion, and still inside of the VM directory. And the files that SW4 is going to spit out are these files, model files. And these model files are actually binary, right? So I cannot actually show the content of the file in the terminal, but those files are going to be used for storing the material properties on each of the recording grid, right? So I have a bunch of recording grid that's generated. That's generated by the URG code already, right? And then MDL, those files are going to store the VPVS, the PS velocities. If I'm doing attenuation inversion, then it's going to store QP and QS, right, on those recording grids, right? So depending upon whether attenuation is considered, the files can be different, right? So for each of the recording grid, it's going to have like 3 numbers for the elastic case, VPBS and density, and then for the inelastic case or attenuation case, then it's going to have like 5 numbers for each recording grid, including QP and QS, right? And those model files are actually the reference model that can be that's needed in order to compute the kernels, the data sensitivity kernels, right? Yeah. So when write info equals to either 1 or 2, SW4 are not going to run to the finish. It's not going to sort of generate all the wave fields or synthetic Southern worms, right? It's just going to spit out all those intermediate files that's going to be used later on for the inversion, right? And the simulation time is supposed to be very, very short, right? Because it's not really carrying out the wave propagation simulation at all. It's just it hasn't entered the time stepping loop yet. So it should finish in like a very short amount of time, right? And then after these two sets of all these files, all these kind of files are created, we can increase the write info number to 3, right? We can increase the write info number to 3, and this time it's going to start to do the time stepping loop, and create all the wave field files, right? And then this time it's going to run to the finish, right? And so the runtime, the work clock time is going to be a lot longer than when write info equals to 1 or 2, right? That's write info. NT-skip is for storing, is a number that's so the URG code is going to generate the spatial recording grid, right? But usually you don't really have to actually store every time step when we actually compute the kernels. The kernel calculation actually involves a temporal convolution, and the convolution is usually a filtering operation. So 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 NT skip is just telling SW4 how many time steps I can skip before sort of saving all the strand fields and velocity fields, that kind of thing, right? So if NT skip equals to 1, that means I'm gonna store every time step, right? If NT skip equals to 2, so I'm gonna store every other time step, so it's gonna skip 1. And if NT skip equals to like 3, then it's gonna store the 0th time step, the 3rd time step, the 6th time step, that kind of thing, right? Has ATT has attenuation or not? If it's 0, then it's elastic. If it's 1, then there's attenuation. And then model path, that's the VM path, that's the complete path. It has to be the complete path. And IPAR flag 2. So IPAR flag is a flag number that's gonna indicate what kind of kernels I'm gonna compute, right? So 2 means that I'm gonna compute the kernels with respect to P and S velocities. It's got a range of values, right? Depending upon anisotropy and that things. So IPAR flag can be kind of very different, right? So for now, 2 is kind of implemented, right? And for other flag values, I haven't actually got the time to actually implement those. And then IK flag has to be specified after the IPAR flag. IK flag is a kernel flag. What kind of kernels you want to compute? So usually it follows for IPAR flag equals to 2, which means that I'm computing kernels for VP, VS, and density, right? But in this case, I don't want to compute the kernels for density yet, because the code for computing density hasn't been implemented yet, right? So if that's the case, I just want to compute the kernels for VP and VS, skip density, right? So the density kernel is going to be the flag for density kernel is going to be 0, right? And then NX skip, NY skip, and NZ skip are actually the decimation rate for the recording grid. So when I was running the URG code, the first command line input was actually this inversion file, right? imv.in, right? And then the URG code actually is going to read these 3 lines. And I use the decimation rate in the X, Y, and Z direction to actually create the recording grid. So here I'm actually saving every other grid in the X, Y, and Z directions, right? So decimation rate is like 2. And for now, the imv.in file is relatively straightforward, right? It's not too complicated. Later on, once we start to actually introduce interfaces or horizons inside the model, then the imv.in file could become slightly more complicated. But for now, for our half space experiment, this kind of information is kind of sufficient, right? So once I have increased the IMV, once I have increased the write info to like 3, I can actually run the simulation to the end. And then let's look at the simulation, the job script. The job script on Xiaoyan, I was using a C shell, so that's gonna give me the job script. So here on Xiaoyan, we have to actually call this code to invoke the to run the parallel code. So SW4, that's 2.0 optimized. But I made some further changes to SW4. Right. Last time I was kind of sort of talking about the fix to the source time function, right? So that's some slight modifications, right? And then I added some codes to read some codes in SW4 to actually read the inversion input file, the imv.in file, right? And then also the code for creating all the outputs, or write out all those outputs in the model directory, and then also the outputs for creating the strand fields outputs, right? So this SW4 is actually a modified version. It's not the original version that's downloaded from GitHub, right? And then this SW4 is going to read the input file. And this input file is not related to the inversion. It's needed by SW4, the wave propagation simulation code, and it has its own input format. So if you want to look at the input file for SW4, it's going to look like that. File IO path. So all the output files are going to be written into this particular directory. So this is event specific, so it's going to be written into FWF, and then followed by the source ID. Parallel file system equals to 1, so it's going to be a parallel MPI output. Verbose to print cycle 10. Print cycle just means that every 10 time steps it's going to print out some kind of a verbose information, that kind of thing. And then the grid keyword specifies the mesh. Right, so H means grid spacing, so I'm using a uniform grid spacing with 200 meter grid spacing. And X, the number of grid points in the X direction, 351. And Y, the number of grid points in the Y direction, that's 151. And then NZ, 250. So the depth is 250 times 200 meters. Right, and then every line starts with a hash is ignored by SW4. So this line is going to be ignored by SW4. And then block is one of the ways for specifying the velocity model. Right. So if I'm using a uniform half-space model, then the velocity doesn't actually change with location. So VP is going to be 6.5 km per second throughout the entire model, and the VS is going to be 3.5 km per second. And then density is going to be 3000. And then the simulation time, the synthetic seismogram is going to be like 15 seconds long, right? And then the location of the source is going to be located at this particular position, right? So it's like a 18.8 km. Y is like 14.9 km. And then Z is at 24 km depth. And then it's an explosive source. So MXX, MYY, and MZZ are equal to each other. And then all of them are equals to 1 times 10 to the 15th power, right? And the type of the source time function, I'm using a built-in source time function that's integrated Gaussian. And then the integrated Gaussian is going to have a sort of average the central time that's like 1 second, and then dominant frequency is like 7.746 hertz. And then I have a receiver that's located at 51 km, x equals to 51 km, y equals to 14.9 km. So it's the y coordinate is the same as the source, right? And then the z coordinate is also the same as the source. The only difference is in the x coordinate, right? And then the output file, the synthetic seismogram, are going to be written into this this particular output file. And then the variables I'm going to be writing into those output files is going to be the velocity. It's going to be the velocity inside of. It's going to be the velocity at this particular receiver, right? Do I want a USGS format? I want a USGS format, right? It's going to write every time step. So the synthetic seismogram is going to be stored at every time step. It's not going to be decimated in any way, right? It's unlike those stream views. The stream views are going to be decimated according to NTSKP that's inside of the imv.in file, right? And that's pretty much it. Once I have this input file, submit the job, it's going to run, right? It's going to run. And then it's going to generate those stream views. And then it's also going to generate a synthetic seismogram file that's called in.rc01.txt, right? in.rc01 is actually the file output, the prefix that I specified here. So this is going to be a text file that's going to be that's storing the synthetic seismogram at this particular receiver location, and it's in the USGS format. So if I want to sort of take a look at this particular file, that's going to look like that, right? It's got a bunch of header information, and then so it's going to have like a few different columns after the header information, right? And then the first column is like the time, and then x, y, and z. That's velocity in the 3 directions, right? And the velocities are in meter per second. And if we want to sort of look at this particular file, we can actually plot it in MATLAB using a code provided by SW4. It's called read USGS, I think. So T. Yeah, that's how you actually use the read USGS code provided by SW4, right? And then if I if I want to make a plot of it, suppose I want to subplot or 3 plot t vx, x is tight. That's going to be the x velocity, the velocity in the x direction, I mean, at the receiver location, right? And then subplot 312 vy, and then 13 vz, right? You can sort of see that the scale is actually very, very different, right? So most of the energy is actually on the x and the z direction. So that's 10 to the minus 5. On the y direction, it's like 100 times smaller, right? So it's like 10 to the minus 7 here. Yeah, that's some nice looking velocity diagrams, right? And the shape of the pulses actually is determined by the shape of the source time function. We have used a Gaussian int. It's an integrated Gaussian. So the velocity diagrams are going to look like a derivative of the Gaussian, right? Yeah. So that's the forward simulation from the source to the receiver, and also the wave field files, the stream field files are those files, WF, these files, right? So these files are binary, so I cannot actually look at them on a terminal. So, but the kernel code are going to use those stream field files to compute the kernel, right? So this is from the source, and then go to the receiver directory. So the receiver directory is actually component dependent. So what I'm trying to do is to actually compute the kernels for the X component, for the waves that's arriving on the X component of the receiver. So that's why I have a FWF directory, subdirectory called in.rc01.x. So this is actually computing the Green's tensors for the X component of this particular receiver, right? So if I go into that directory, all the files are kind of similar to the folder directory that's coming from the source, right? But you're gonna see a different input file. That's the input file, right? So if I look at the input file to SW4, the grid information is the same. The output file directory, the output directory is different now, right? And then the source is going to be something that's kind of different, right? The source is going to be at the location of the receiver, right? So the source is at 51 km, x equals to 51, y equals to 14.9, z equals to 24, right? And then if you still remember, right, that's the receiver. This is the input file for the source 10001, right? And then the receiver is at this particular location. Now the source for the receiver directory, for RGT or receiver green tensor directory, the source is at this receiver location of the so it's a virtual source that's located at the location of the receiver, right? 51 km, 14.9 km, 24 km, right? And then the body force is going to be a single force that's pointing to the x direction. So Fx is going to equal to 1.0, and then Fy and Fz are going to be 0. And then F0 is going to be equal to 1. So the scalar moment is like a 1, right? So there's no scalar moment. The scalar moment is 1, so there's no scaling to it. And then the source time function is something that's specified by myself, right? And this source time function was used as the example in my last video when I was trying to explain the fixed source time function. So now the code actually works. Now the code actually works with a user specified source time function, right? It's just an ordinary text file with some kind of a special format to it. And then everything else are going to be pretty much identical to the input file of the actual source, right? And then I can just run the code, run SW4, right? Run SW4, it's going to create all those stream field outputs, right? And then if you want to look at the synthetic cytogram at the actual source location, you can specify a receiver at the location of the source, basically. So, right. So the receiver location is actually at the source, the actual source location. So you can sort of compare them, right? And then after these two simulations are done, the next step is to run a different code. It's actually, well, the next step is actually to pick the windows, to pick the time windows. That's going to be used for isolating the specific arrivals you want to compute the kernels for. Right. So how do we actually pick the arrivals? Suppose we're actually looking at this particular component, right? We have like 3 arrivals here. This is a direct arriving P. This is a surface reflected P, and this is a surface converted P to S converted wave, right? We have like 3 different arrivals. So if we want to compute the kernels for all 3 waves, then we have to actually come up with 3 time windows to isolate each of the individual arrivals, right? But the thing is that when we pick the time window, it has to be a time window for the arrival that has been filtered by the source time function used for computing the receiver green tensors. Right. So the receiver green tensor is not really a green tensor, right? It's a filtered green tensor. Why it's a filtered green tensor? Because the source time function. The source time function is not exactly an impulse. It's a low-pass filter. It's a low-pass filter with a corner at 2 Hz, actually. It's a Butterworth low-pass filter with a corner at 2 Hz. Right. So the reason that we have to use some kind of low-pass filter or some kind of bandpass filter is because the spatial mesh doesn't actually support us to actually compute the Green's function to infinite frequency, right? The Green's function is supposed to be computed for impulse or direct source, right? But for a direct source has infinite frequency, has energy at infinite frequency, right? And it's impossible to actually compute a numerical solution for infinite frequency, right? The grid spacing will have to be like 0, right? But so we have to actually use a source time function that's kind of a band limited, right? And when we compute the kernels, we have to actually account for the fact that the Green's function is not really a Green's function. It's a low-pass filtered Green's function. So we have to actually filter the synthetic cytogram with the source time function used for computing the receiver green tensors, right? So you have to actually filter this cytogram with the source time function used for computing the RGTs, and then the source time function used for computing the RGTs, you can get that from this particular file, right? But this file is usually sampled on a different time sampling interval from the SW4 time stepping step length, right? The source time function that has been resampled to the simulation time steps is g1.dat. That's one of the outputs generated by SW4. So all we have to do is to actually convolve this cytogram with the second column of g1.dat. Why it's the second column? Because so if we look at g1.dat, the first column is actually the time step, the time sampling, the time column. The second column is actually the source time function, but resampled using spline interpolation, right, to this particular time sampling sequence. But the third column is actually the time derivative of the second column, and then last column is actually the second order time derivative of the source time function. So if we want to get the source time function and it's actually sampled to the same sort of sampling interval as the SW4 for the wave propagation simulations, then all we have to do is to convolve the second column of g1.dat with the synthetic hardware. And so if I want to sort of load the g1.dat, I can just load the g1.dat, right? And then so if I want to look at it, so I can make a plot of it, the first column and then the second column, right? That's a Butterworth bandpass low-pass filter. You can sort of see that it has a non-zero phase, right? So it's not a zero-phase filter, but it's a minimal phase filter. It's a minimal phase filter. So all we have to do is to actually convolve this particular curve to with this particular curve, right? And then after the convolution is done, so let's call it a CV x equals to conv. This is doing the convolution in MATLAB, right? And let's just do a convolution, and then we can just plot it. T CV x1 to the length of t. Right. After filtering, the x component is going to look like that, and then the time window has to be picked based upon this filtered synthetic hardware. Right. So if I want to sort of pick a time window for the direct deriving p, you have to like pick like 4 different data points, 4 different time locations, right? Because it's a cosine taper, so it's flat in the middle and then tapers down on the side. Right. So for direct deriving p, a good taper might be 4.5 to 5.5, and then 7 to like 8, or 7.5 to like 8.5, that kind of thing. That gives you a good taper, right? And then for the middle window, it's gonna be a different time window, and then for the last phase, it's gonna be a different time window. So if we want to pick like 3 different windows, we have to pick them on the filtered synthetic hardware, right? And then the picked windows are going to be stored inside of a text file. And this text file is supposed to be inside of this for the simulation directory of the event of the earthquake, right? And this particular file is going to be named like that. It's going to be named like this thing. It's the file name of the synthetic seismograms followed by .win, right? That's the window file. So if I want to look at this particular window file, it's going to have 3 lines inside of it. That's the 3 time windows. So this is the window for P. This is the window for time window for PP, and then this is the time window for PS, right? So I've got like 3 different time windows. And this file is actually generated by hand. For this particular example, it's generated by hand, right? But for some other, for realistic inversions, those windows may have to be picked by kind of automatically or somehow, right? So we've got like 3 different windows. And once we got this file, once we got this window file, the next step is to compute the wave field perturbation kernel. So that's the wave field perturbation kernel. In my previous publications, I was calling it seismogram perturbation kernel, or SPK, but now I am renaming it called wave field perturbation kernel. The wave field perturbation kernel is just the Fourier derivative of the misfit measurement with respect to the seismograms, right? And there's a code for doing that, and this code is called WPK. So this is the shell script calling the binary WPK.CSH. Let me look at its content. Right. So that's the name of the binary called WPK wave field perturbation kernel. So it's going to take a few command line inputs. The first command line input is a text file that's containing a list of all the different windows. Right. It's a text file. It's a text file. If I look at the content of it, so this text file is this file. It's basically this file. If I look at the content of it, it's wing LSD, and then it's gonna give me that's the complete path to that window file that I was just I was just showing you, these 3 lines, right? And then followed by the component on which those windows are picked, right? So it's the X component, right? So the window list file is just this kind of text file, right? It's the window file followed by the component of that particular window. That's the first command line input to WPK. And then the second command line input is actually the source time function of the RGTs. The source time function used for computing the receiver green tensors. Usually this file is actually like fixed for every receiver, right? So for the entire inversion, this particular file is kind of fixed. It's not really changing at all, right? So you can just pick like an arbitrary receiver and then use that g1.dat file as the source time function file, right? And then there are 4 numbers here, right? The 4 numbers are actually, the first number is actually specifying which column I'm supposed to use for the g1.dat file, right? I was saying the g1.dat file has like 4 different columns, right? So the 0th column is actually the time column. The first column is actually the source time function. So I have to specify the first column here, right? And then the next number is actually the type of the wave provision of the WPK, right? So if you are computing the kernels for broadband cross-correlation travel time, then this number is supposed to be 1, right? And if you are computing frequency-dependent group delay, then this number is supposed to be 2, right? So for different kinds of misfit measurement, the WPK has to be computed accordingly for different kinds of misfit measurements. And this number is just basically for indicating which kind of a misfit measurement I'm actually using, and then what the WPK is supposed to be, right? And then for broadband cross-correlation travel time, there are some kind of subtle differences, right? So in the original paper by Li Zhao and also the Tony Dallin and earlier papers, the broadband cross-correlation travel time measurement was made on displacement seismograms, right? But displacement seismograms kind of has a problem with near field terms, right? Those near field terms tends to give you this kind of a non-zero mean, right? It's not as isolated as the velocity seismograms. So on a velocity seismograms, all those kind of a non-zero mean is going to be kind of canceled out because you are taking a derivative. All those all those non-zero mean are going to be kind of become 0 after you're taking a derivative. So usually if you want to sort of make measurements, you might want to sort of use a velocity seismogram, right? So in order to actually compute the kernels for broadband velocity, for cross-correlation measurements on broadband velocity seismograms, then the WPK has to be computed slightly differently, right? And then you have to account for the fact that the seismogram you are using is actually the velocity seismogram. It's not displacement seismogram, right? And so for now, in my code, this flag is actually based upon the idea that the cross-correlation was made, the cross-correlation misfit measurement was made on a velocity seismogram, and then the seismogram that's used for computing the WPK is also a velocity seismogram, right? I do have the code. I have finished I have the code for the original case in which the cross-correlation was measured on the displacement seismogram, and then the WPK was computed using velocity seismogram, right? That code is actually easier. I have that code. It's inside of the WPK code, but I haven't actually exposed that code to the user yet. So at some point I may want to sort of add one more flag just to allow the user to compute the WPK for that particular case. And then the next 2 numbers is actually the beginning time sample. This number is actually the beginning time sample I want to write out for the WPK. So WPK are actually time series. I want to write starting from the second time sample, and then 1 is actually the time sampling interval. of the WPK, right? So I don't want to skip any time samples. So if I want to have a time decimation rate, then this number should be larger than 1, right? 1 means there's no decimation in time sample. Why it has to be 2, right? Why it's not 0? Right? In my previous kernel check video, I was trying, I have found this kind of problem. I have no idea why, but I'm still actually investigating why it has to be 2. I have to actually start writing the WPK at the second sample. So I'm basically skipping 2 time samples, the zeros and the first time sample, right? If I start writing at the zeros time sample, then the kernel won't look right. The kernel will have problems. The kernel is not going to have a zero sensitivity on the rate path. It's going to have blue sensitivity on the rate path. That's incorrect, right? But if I actually shift by, if I actually get rid of the first 2 time samples, then the kernel is going to look right. But exactly why do I have to do that? I haven't actually figured out yet. Right. So all I have to do is to run this WPK code with this bunch of inputs, and then it's going to create a WPK file. It's going to create a WPK file, and this WPK file is going to be this particular file, right? So if I go back to the simulation directory, for the simulation directory, I'm going to see the output, right? And this output file is just going to be a text file, and with 3 columns basically, right? The reason it has 3 columns is because we have 3 time windows inside of that window file, and then each window is going to generate 1 WPK. The first 2 rows is actually the time the time sample within which the WPK is non-zero, right? It has a non-zero value, right? And then all the rest of the file is going to be dominated by zeros, right? And within this particular time sample range, then it's going to have a non-zero value. So for the first column, for the first window, it's going to range from like 140th sample to like a 250th sample, right? That's the non-zero values of the WPK. And then for the second time window, it's going to go from the non-zero values are going to be inside of the are going to be from 265th sample to 375th sample, that kind of thing, right? And then once we got this particular WPK file, we have to create a kernel directory, right? So we have to, if the kernel directory is not created already, you have to create it, right? Either by using a script or manually. So inside of this kernel directory, it's organized like this. So this is the event, the source, the actual source. And then inside this actual source, you're going to have receiver directories. Also, depending upon the components, right? That's the receiver directory. And then inside of the receiver directory, we're going to have a soft link to that particular WPK file that we just generated. Right, so if we look at this particular link, it's a soft link. It's actually pointing to that WPK file. So this soft link has to be there, right? And then that's the only file that's needed inside of this kernel directory in order to actually run the kernel code, right? So now we can actually go run the kernel code. The job scripting is inside of the jobs directory, and then the kernel code is called inside of this particular job script. It's called dsk run dsk.css. Sorry, it's a parallel code, so we have to actually use a job script to execute it. So for now, the number of processes used for computing the kernel, it doesn't have to be exactly the same as the number of processes used for doing the forward simulations, but I haven't actually done a thorough testing if you actually change the process, the number of processes. Right. I suppose it's okay to actually have a process number that's smaller than the number of processes used for the simulations, but I don't know if it's going to be okay if the number of processes is going to be larger than the number of processes used for the simulations. Right? I don't know. I haven't tested it. And then the kernel code is called the binary. The kernel binary is going to call it is called DSK, data sensitivity kernel. DSK stands for data sensitivity kernel. And then it's going to take the inversion file in inv.in, the complete path of it. And then it's going to take the directory for the forward wave progression simulation code for directories, FWF, right, the complete path. And then it's going to take a list of the WPK files. So this WPK LST file is just a text file. So it's right here, right? It's just a list of all the WPK files. But one of the things that I have to pay attention to is that it's actually the complete path to the soft link inside of the kernel directory, right? It's not the original text file that's inside of the forward simulation directory, forward wave field directory, right? It has to be the soft link, the complete path to of the soft link inside of the kernel directory, because that's how the DSK code actually deciphers the forward simulation event ID and the receiver ID from this particular directory structure, from the path of the WPK file. And then the last input is going to be the kernel output directory, And then 1 means I want to just compute the volume kernel, right? So the DSK code can also compute the surface kernel. So if we want to change the topography of one of the internal horizons, that kind of thing, we can change that to 2, right? And if we want to both the volume kernels and the surface kernels, then it's 3, right? So this is just a flag indicating what kind of kernels I want to compute. So I can just submit this job, and then after it's finished running, it's gonna create all those KV files. KV means it's volume kernel, right? And then if it's a surface kernel, it's going to be called KS followed by the process ID, right? And all those kernel file output files are actually binary. If I want to make a plot of it, if I want to sort of look at some plots of the kernels, I have to use another sequential code, which is called AVK. And I have a shell script that's calling the AVK binary. That's how we call it. AVK means assemble volume kernel, right? And then the first command line input is the inversion file, and then we will need the WPK that's used for computing the kernel. The WPK file used for computing the kernel, and then the kernel directory where all the KV files, binary KV files, are stored. And then this particular file is actually specifying what kind of cross sections we want to extract. It's also a text file. I will try to explain the text file format in a little bit. And then the last command line input is actually the output directory, or the prefix of the output files. So you can sort of see you have kv underscore all, and then followed by some numbers, that kind of thing. So those files are actually text files that you can actually plot using MATLAB, right? And then those are actually cross sections, right? You can sort of imagine what the x and y actually means, right? So this is the cross section at x equals to 88. This is the after decimation. So this is actually the x grid number after decimation. Don't forget, the INV file actually specifies the decimation, right? It's in the x direction, it's like 2, right? So x equals to 88 means what? X equals to 88 means how many grid points we have for the simulations. It's in the x direction, it's 351, I think. Right. So in the x direction, it's like 351, right? So after decimation, 351 divided by 2, we have 175. So in the recording grid number in the x direction is 175, and then if you divide by 2, then it's like 87, right? 87. 88 is just like one grid over to the so because this is zero-based index, right? If I just do this kind of tool, but SW4 actually uses one-based index. So 88 is actually 87 here. So x equals to 88 means that I want to take a cross section that's right in the middle of the x grid of the recording grid. Right. Y equals to 38. That's also for decimated grid, right? So all those things are actually specified inside of this text file called kv_xsc. So let's look at its content, right? Let's just do a cat kv_xsc, right? So for different types of kernels, so the first column, the first number is going to specify the kernel ID, right? So 0 means it's a P kernel, 1 means it's an S kernel. And then you can imagine if we have the code for computing the density kernel, then the density kernel is going to be 2, right? And then if we have anisotropy, that kind of thing, so it's going to be more different kinds of kernels, right? So the first number is always going to be the kernel ID. The second number is going to be the WPK ID. So don't forget we have like 3 different windows, right? 3 different waves. So 0 is going to be for the direct deriving P. That's the first window in our window file. 1 is going to be the second window, right? Second window is in our case it's the PP, right? And then the second window, the third window, the last window is going to be the PS converted wave. And then X, Y, those kind of things are actually specifying the cross section where we want the cross section to be located. So we want the cross section to be located at Y equals to 38. That's the after decimation, the recording grid. Recording grid number for Y equals to 38. Recording grid number for X equals to 88. That kind of thing, right? So recording grid number Y equals to 38 is actually right in the middle of the volume. Right, it's going through both the source and the receiver. It's the source-receiver plane, right? That's kind of perpendicular to the free surface, right? So that's the text file for specifying the cross sections. So once we have finished writing this particular input file, we can just call the avk. Right here, I have avk. .csh. It's gonna run, and then it's gonna tell me the screen output of this particular code is gonna tell me the dimension of each of the cross sections. Each cross section is basically just a matrix. It's telling me that for the first cross section, the grid 0, I only have like one grid, right? But if I have like a multiple grid, it's going to tell me the dimension for each of the subgrid, right? It's going to be nx and nz. Ax is going to be 176, and then nz is going to be 125. So it's going to be a matrix with 176 rows and 125 columns. The thing is that nz is going to be the fast direction, and x is going to be the slow direction. So all the different z's for the same x is going to be stored together, right? So once we actually go back to MATLAB and try to plot it, this particular file is actually a one-column file, right? And then we have to reshape that one-column file into this kind of two-dimensional matrix. And then we have to pay attention to MATLAB's convention about what's actually the fast direction and what's actually the slow direction. So that's the sort of supposed to be the dimension of the matrix, right? And then all those output files are going to be stored inside of those files, kv_all dot. So this first number is going to be the kernel ID. 0 means VP kernel, 1 means VS kernel, right? And then the second number is the WPK ID. So 0 means it's a direct deriving P. 1 means it's a PP, and then 2 means it's a PS. Right, so depending upon how you organize the windows in the window file, and then x equals to y equals, those are the grid locations, the locations of the cross sections, basically, right? And then all we have to do is to actually plot them inside of MATLAB, right? So how do we actually do that? So small k equals to load, right? So that's more like that's one of the examples, right? So I'm loading this particular kv underscore o 00. So it's the p kernel for the directory in p for the cross section that's located at x equal to 88, right? Small k is going to be a one column vector, and then I'm reshaping it. I'm reshaping it to a two-dimensional matrix, right? And then the dimension I want to specify is fast direction followed by slow direction. The fast direction is going to be what? The fast direction is going to be uh, that's this particular cross section, right? So the fast direction is going to be 125 because the NZ is faster. So fast direction is 125, and then slow direction is going to be NY 76, right? And then if I just run that, it's going to create a K26. 26 is going to be a two-dimensional matrix with this many rows, this many columns, right? And then if I want to make a plot of it, it's going to look like that. So I can do a p color, right? K26 shading flat color map. I'm using this particular JETWR color map. This kind of color map is kind of consistent in all our previous publications. So red means negative sensitivity, blue means positive sensitivity, and then white means zero sensitivity. So you can see the donut hole here, right? It's zero sensitivity right in the middle of the, right on the ray path, source receiver ray path. Axis equal axis tight. So C axis goes from like a 10 to the minus 8 to minus 10 to the minus 8 to positive 10 to the minus 8, and then the YDR reverse. So SW4 has a convention that the Z point is positive downward, right? So that's why I have to sort of reverse the Y direction, right? So basically that's how the kernels are computed, right? If you want to look at the other cross sections, all those other cross sections are being plotted here, right? So for the simulation that I have just was showing you, the kernel are supposed to look like that, right? And here it comes with some of the differences compared with kernels computed with AWP, right? It's probably related to the boundary conditions or the absorbing boundary conditions or the perfectly matched layer absorbing boundary conditions. In SW4, it's called a supergrid or something, right? Supergrid is supposed to be kind of equivalent to the perfectly matched layer, right? But the problem is that so on the top row, it's the kernels computed using a smaller grid. The volume of the grid is kind of smaller. So here you can sort of see it, right? So the horizontal axis goes from like 1 to like 150 something. Here it goes from 1 to like 170 something, right? So the simulation domain for the bottom row is larger than the simulation domain for the top row, right? And here, for the direct deriving P, you don't really see much of a difference, right? Except for maybe the plot is kind of scaled differently, right? But if you actually make the plot in the same kind of range, then they should look almost identical. So for the direct deriving P, you don't see much of a difference. But for this surface reflected P, PP, you sort of see this kind of boundaries here, right? These kind of rectangular boundaries, which means that the waves that's hitting the boundaries, those glazing passing those supposed to be absorbing boundaries, are not being absorbed very well by the absorbing boundary condition. So you still have some kind of residual, which gives you very high sensitivities here. But these high sensitivities are not real, right? So when we actually do the inversion, we actually have to cut off this part of the volume. We have to get rid of it, right? This is something that I didn't see in the AWP code. The AWP code actually implements the perfectly matched layer or PML boundary condition. And the PML boundary condition is actually quite good inside of the AWP code. You don't see this kind of a very high sensitivity close to the absorbing boundaries, right? But if I enlarge the entire simulation domain to this kind of a larger size, so here for this particular simulation, the source and receiver is about 50 grid points, or let's see, it's about 75 grid points or 50 grid points to the absorbing boundary, I think. Here it's like 100 grid points to the boundary, right? So for this particular domain, it's like the source and receiver is like 100 grid points from the nearest absorbing boundary, right? So here you can sort of see this kind of egg-shaped shape. This is actually the correct sensitivity if we want to include those were the effect of the contributions of those waves, right? But if I reduce the simulation volume, you're supposed to actually get a truncation, right? You're supposed to get a truncation at those boundaries. But in reality, SW4 is not giving you zero sensitivity here. It's giving you this kind of enhanced sensitivity, right? Which means what? Which means that if we want to use those kind of multiply scattered waves, which usually has a quite large domain of sensitivity, we probably have to make our simulation domain even wider than AWP. Simulation domain has to be larger than AWP in order to actually avoid any kind of bias during the inversion. Or another choice is to actually make sure that when we actually do the inversion, all those boundary sensitivities are getting truncated. Just get rid of those sensitivities, right? That's another solution. That's another sort of fix, right? Yeah, I'm gonna end this video here. So next time, let's try to do more kernel examples. Let's do some surface wave kernels and then head wave kernels, that kind of thing. Let me end this video here.